Today's episode isn't about individual discoveries, it's about a shift in how science views reality as a whole. In ecology, neuroscience, astrophysics, and the theory of complex systems, scientists are increasingly coming to the same conclusion. The world is defined not by objects themselves, but by the connections between them. And we'll start with a discovery that especially changes our understanding of stability and why complex systems can suddenly collapse. For a long time, it was believed that if an ecosystem appears stable, species are present, biomass is maintained, then everything is fine with it. But in recent years, researchers have increasingly encountered a paradox. A system can remain outwardly calm and yet suddenly collapse without any apparent reason. It turns out that the signs of an impending crisis are hidden not in average indicators, but in the loss of internal flexibility. An ecosystem gradually loses its ability to adapt to disturbances, even if this is almost unnoticeable on the surface. It's like a house with intact walls and a roof, but with a foundation that has already cracked. Recent studies show that the classic early warning signals of an approaching tipping point, such as increased fluctuations and slower recovery after stress, do not work well with real-world natural data. It's as if the fire alarm sensors only go off when the flames have already reached the ceiling. And in a rapidly changing environment, such signals may appear too late when the process has already become irreversible. That's why the focus is now shifting. Instead of looking only at the state of the ecosystem, scientists are increasingly analyzing the structure of connections within it. Not just which species are present, but exactly how they interact with each other. It's not about how much energy is in the system, but how it is redistributed through the network of trophic and symbiotic relationships. Resilience turns out to be a property not of the elements themselves, but of the architecture of interactions between them. A similar shift is happening in our understanding of how the human brain works. It used to be believed that in uncertain conditions, a person acts like a rational calculator, assessing probabilities, weighing risks, and choosing the optimal option. But modern research shows that the brain almost never works this way. Instead of searching for the best answer, it does something else. It restructures its very model of the world to fit the current task. The brain continuously predicts what will happen next and tries to minimize not the error itself, but the element of surprise. In this context, thinking becomes a process of constant adaptation, not calculation. Recent studies show that the same person can be coldly rational in one situation and intuitively impulsive in another. And this is not a contradiction, but a sign of flexibility. Different strategies prove useful in different contexts, and the brain switches between them freely. It's important to understand, irrationality here is not a malfunction, but an adaptive mechanism. It is precisely these principles that now form the basis of new artificial intelligence architectures. These are systems that not only optimize answers, but also dynamically restructure their understanding of the task and environment. The shift toward analyzing connections is also evident in astrophysics. For a long time, interstellar dust was considered a secondary byproduct, something like cosmic debris left over after stellar explosions. But observations from modern telescopes have radically changed this picture. It turned out that dust forms much faster than previously thought and plays an active role in the evolution of galaxies, especially in the early universe. It efficiently cools gas, promotes its compression, and triggers star formation processes billions of years earlier than previous models predicted. In fact, dust turns out to be not just a background, but one of the main regulators of cosmic evolution. It's not the stars that shape the environment, but the environment that sets the conditions in which stars can form at all. And once again, the key is not the object itself, but the system of interactions. Modern complex systems theory takes this idea even further. Researchers are increasingly finding the same mathematical patterns at vastly different scales. The metabolism of living organisms, the energy consumption of cities, the training of neural networks, and even the behavior of quantum systems all follow similar power law relationships. Beneath the apparent chaos lies a universal statistical structure. This explains why complex systems, despite having a huge number of elements, often behave not randomly, but according to a limited set of scenarios. Their dynamics are determined not by the details, but by the overall architecture of connections. All the topics in this episode converge on one point. Reality is revealed not in individual points, but in the lines between them. Connection turns out to be more important than composition, context more important than content, structure more important than parts. Modern science is less and less often searching for the main element and more often studying how elements are connected to each other. It is in this shift that the deepest changes in our understanding of the world are happening today. That was the science news. Thank you for your attention. See you in the next episode.